AQA A Level Physics, Gravitational Potential. This bit of the syllabus. Okay, start with a question. How much gravitational potential energy does a 1 kilogram mass have at the surface of the Earth? And the answer isn't zero, not on a universal scale. It's not zero, it is minus 62.5 million joules. Okay, 62.5 million joules minus. So it has negative gravitational potential energy, and that's rather a lot. Now, how come it's got minus 62.5 megajoules of energy, gravitational potential energy? Because if I got a kilogram on the surface of the Earth, and if I wanted it to escape from the Earth, if I wanted it to get to now infinity, it's like imaginary place where it's completely billions and billions of miles away from absolutely everything. It's, you know, away from the Earth, a ridiculous distance away from the Earth. And if I want to get my kilogram from the Earth to infinity, then I have to do work. And I have to do 62.5 megajoules of work to get a kilogram from the surface of the Earth to infinity. Okay, to completely escape from the Earth's gravitational field. That's how much work I would have to do. Because 1 kilogram at infinity would have zero gravitational potential energy. I mean, why should it have any? It's not in any gravitational fields. So on Earth, it would have negative potential energy. Because we would have to do work to get it from Earth to infinity, and if at infinity it has zero, then on the surface of the Earth it must be negative. So gravitational potential energy is actually negative. Yeah, in our solar system around the Earth, it's a negative quantity. Okay, this idea in physics, we are in a potential well. Imagine, you know, somebody's dug this hole in the ground, and that's us there on Earth. We're at the bottom of a well, and to climb out of the well, we have to do work to climb out of the well, to escape from the Earth's gravitational field. Look there. Oh, we're nearly there. We're heading towards infinity. If we actually get to infinity, then we have escaped from this gravitational well, this potential well. Just imagine, you know, it's actually an awful lot of work required to escape from the Earth's field. Just imagine this rocket is going to the moon and how much fuel it needs to actually get away from the Earth is a huge amount. This is a Saturn V rocket which went to the moon, and most of the rocket is actually just fuel, carrying fuel, all the different stages. So to escape from the Earth, you have to do an awful lot of work. To get 1 kilogram to infinity is 62.5 million joules of work. This quantity here is called gravitational potential, and it's a negative quantity. V is minus gm over r. And that tells us at any point in space how much work you would have to do to get a kilogram from there to infinity. I know that's not the formal definition, but I think that's the most useful way of thinking about it. So remember it's negative, and remember it's joules per kilogram. Yeah, it's the amount of work you would need to do to get a kilogram from a certain place to infinity. So the gravitational potential at the surface of the Earth is minus 62.5 times 10 to the 6 joules per kilogram. The gravitational potential at a point in space, due to the Earth being there, big M there is the mass of the Earth, because it is creating the well, is how much gravitational potential energy 1 kilogram would have at that point. So it's negative. It's measured in joules per kilogram. Okay, Hopefully you understand why it is a negative quantity. And also notice that it's an inverse relationship with R, not inverse square. You will remember that little g is gm over r squared, okay? V, gravitational potential, is minus gm over r. It's not inverse square, it's just, oh, that should be squared. Yeah, it's not inverse square, it's just inverse. A satellite of mass 45 kilograms is to be put into an orbit which has a radius of 12,000 kilometers. Calculate its gain in GPE. So we want to get a satellite from there to there. Let's not worry about the kinetic energy of the satellite yet. Let's just think about the gain in GPE. Now, how much work would we have to do to get my satellite from A to B? Now, we can't use MGH. Why can't we use MGH? Because G isn't constant. I mean, at the surface of the Earth, G is 9.8. At this particular radius, G is, I don't know. But it is not constant, and we can't use an average because it doesn't go down linearly. Okay, so we need another way of doing it. And the way we do it is we say that the change in GPE, or the work you would have to do, or the energy transferred, is m times delta V. The difference in potential. You've got the potential at the surface of the Earth, you've got the potential at this particular radius, and the difference between them is delta V. Yeah, if you like, the gravitational potential difference. And that's joules per kilogram. So if you multiply it by little m, that tells you the change in gravitational potential energy. And then you do the math, so you work out V there, or you work out V there. You can factorize that equation, okay? And in this particular example, it works out at 1.32 times 10 to the 9 joules. This equation, interestingly, it's analogous to in electricity. Do you remember energy transferred is W equals Q V, or if you like, Q delta V, because it's potential difference. It's the same idea, only this is with masses and gravitational potential. This equation is with charges and electrical potential. Notice that the satellite in orbit would have negative gravitational potential energy, because potential is a negative quantity. It would also have positive kinetic energy, but its total energy would be negative. And how do I know? Because if it wasn't negative, then it would escape. Have a go at this question. Pause the video, pen, paper, calculator, and I'll show you the answer. 3, 2, 1. There you go. So I've worked out the potential at this particular radius. So the potential energy of the satellite is mv, so that the GPE, notice the GPE is negative. I've worked out the kinetic energy is just a half mv squared, and then the total energy is also negative, because if it wasn't, it would escape. You can imagine our gravitational well as being something like that. And then our satellite, one way of thinking about it, our satellite is kind of doing this kind of thing. Yeah, it's got kinetic energy, but it hasn't got enough kinetic energy to escape from the well. What is the relationship between V and G? Well, we've got V is minus gm over r. And we've got little g is gm over r squared. Okay, what's the relationship between them? Well, look at this potential well, and imagine you had to climb out of the well. So that's you at the bottom of the well. And as you climb out of the well, you'll notice that the steepness of the well is getting less and less. Yeah, the gradient Okay, the potential gradient is getting less and less. Now, why is it getting easier and easier to climb out of the well? Because it's getting less steep, because the field is getting weaker. The gravitational field is getting weaker. We have G equals dV dr. dV dr is the slope. It's the rate of change of potential with distance. Yes, it's the gradient. If you've got a graph of V against R, then the gradient is dV dr, tells you the field strength. You should be able to do this if you're doing A-level maths. You know, just differentiate that. And what do you get? Yeah, dV dr. This diagram, these circles represent equipotential surfaces. Because they're all at the same radius, if you looked at any particular circle, like this circle, it's actually a surface, it's a sphere. It's an equipotential surface. And any point on that sphere has the same distance from the center of the Earth, so it has the same potential, so it's an equipotential. Notice on this diagram that the equipotentials get further apart. Why do they get further apart in this non-uniform field? Because basically, if you do a certain amount of work moving away from the Earth, because the field gets weaker and weaker, you'll be able to travel further for the same amount of work. Yeah, for the same potential difference, it will be over a bigger distance. Okay? Because dV dr will be getting smaller because the field is getting weaker. This is another graph. This is a graph of G against R. And the area under this graph is important because the area is, the area is the integral of G with respect to R. That's the area here. And the area is therefore the potential, or the potential difference between two values of R. Okay? Why is it the area? Well, because if you integrate your expression for G, you get V. That's a kind of a mathematical answer. I would also say, remember that work equals force times distance. If you had a graph of force and distance, yeah, if it was a straight line, then the area is the work done, the energy transferred. It's just that the difference here is that it's not a straight line, but the work is still the area underneath, and it's the work per kilogram because G is F over M. So it's like the work per kilogram, and that's delta V, joules per kilogram. This is quite a tricky topic, and it may take you several looks at this video and looking in other books, and hopefully your teachers explained it to you. It's not an easy topic. Remember that if you've got a graph of V against R, then the gradient is the field strength. Remember, if you have a graph of G against R, then the area under the graph is the difference in potential. Okay, I mean, we can say delta V if you like, between two values of R. If one of the values of R is infinity, then we're talking about the total area under the graph all the way to infinity, and the total area under the graph all the way to infinity is the potential at that value of R. Okay.